Hi everyone, Dr. J here, and in this video we're going to talk about some basic multivariate calculus operators. And the first one that we're going to talk about is the gradient of a scalar field. Now before I jump in, let's just quickly review. A scalar is just a number. So we'll write a scalar as a small lowercase letter, and we might, assign it a value. But in this case, we're not talking about just a scalar by itself. We're talking about a scalar field. Could be a 2D field or a 3D field that is going to have a scalar valued quantity. So for example, elevation would be an example of a 2D scalar field. It's in 2D, x and y would be the coordinates, and then at each pixel or at each coordinate value, there's going to be some z, some elevation, and that's just a number. It's just one number, which is the elevation at that location. So we'll give this scalar field a variable name. We'll call it phi. And again, the idea is that it's just one number, but it's a number at each location that we can consider. So whether that's 2D or whether maybe it's 3D, we'll give that we'll give it the representation of phi. So phi is just the value of some scalar field at some location. An example of a scalar field is actually gravitational potential, not the gravity field, or not the gravity acceleration, which is a vector, it has a direction and a magnitude, but the gravity potential. So for example, potential energy, gravitational potential energy, that is going to have just a single value. It's going to be a 3D potential, so it's going to have a value everywhere in 3D space, but it's going to be just one number at each location. Gradient of that scalar field can be written like this. So this upside down triangle is called nabla, so nabla phi. That's the gradient of phi. And because this is a multidimensional field, 2 or 3 dimensional, it's going to have multiple dimensions. And so we can actually write this out as a vector. The key thing here is that this is a partial derivative of phi with respect to x. So this is basically, you're familiar with regular derivatives of a function. This is just the derivative of this function in the x direction. So we're going to take this scalar field, we'll calculate the slope of that field at every point. This is going to be some number which has a value at every point, and it's the slope of phi in the x direction. So if we took a cross section through phi in the x direction, at each point, at each pixel in that field, we would get d phi dx. So we call this d phi dx. That's the partial derivative of phi with respect to x. Now, if this is a 2D field or a 3D field, it's not enough to just say x. We have to say the other dimensions. So for 3D, for example, for the gravitational potential, we would have d phi dx, d phi dy, d phi dz. Your book will write this in a slightly different way. I don't know if you can see that very well, but that's d phi dx I hat plus d phi dy j hat plus d phi dz k hat. So I, j, k are the unit vectors there. Now, this is a perfectly fine way to represent a vector. It's 3 components. These 2 things are exactly the same. So d phi dx, d phi dy, d phi dz. And then the I hat, j hat, and k hat are just saying that these different components are in those x, y, and z directions. I'm not a particular fan of this because it looks like you're adding something together. You're not really adding them together. It's just 3 components of one vector. And so I prefer this notation where you're actually using the vector notation to denote the fact that you have 3 components of this gradient field. So gradient of a scalar field, so again, this is a single valued field at each location, is actually a vector, which means once you take the gradient, you go from being a scalar, a single valued field at each location, to a multi-valued field at each location. So now there are 3 numbers that you need at every single point in space in order to represent the gradient of a scalar field. So we can represent it this way, we can represent it this way, but this would be the gradient of a scalar field. So I'll just put this over here to remind us that this is what the gradient definition is. Now let's talk about divergence. Divergence is a really important quantity, and we can write the divergence as, we'll still use this symbol, this nabla symbol, or we call it del. del, and then we say del dot. Now del dot is actually going to be acting on a vector. So f here would be a vector valued field. So whereas before we had phi, which is a scalar valued field, f is now going to be a vector valued field. Now, this is going to seem a little abstract probably at this point. Once we get into the course more, we'll talk about gravity, we'll talk about magnetics, and these are going to have some physical meaning. So for example, we talked about phi being the gravitational potential. F is going to be some vector valued field, which is going to end up being relevant for gravity and magnetics. And we can take the divergence of that vector valued field by taking the dot product of the del operator with our vector valued field. So this is going to be a dot product. We're going to multiply components together and then sum. So we have partial derivative of f with respect to x plus the partial derivative of f with respect to y plus the partial derivative of f with respect to z. Now you probably are wondering at this point, how is this different from what we just looked at where we had the definition of the gradient with that sum? Well, the difference is that there is no I hat, j hat, and k hat on these terms like there was with the definition of the gradient. So if we add those I hat, j hat, k hat terms in there, then this sum is no longer actually a sum, it's a three-component vector, which again is why I don't really like that summation notation for representing gradients. But here in this case, this is an actual sum. It's an actual sum. It's the divergence operator. It's a dot product of two vector quantities. So the del operator is the three-dimensional derivative. The f is a vector valued field. So we take the divergence, we take del dot f, that's a dot product. And sorry, I've forgotten to add in a very important thing, which is the x component of f. It's going to have x, y, and z components. So the divergence of a vector field f is going to be equal to the product of each derivative operator times that component, summed all up. The partial derivative of fx with respect to x, partial derivative of fy with respect to y, partial derivative of fz with respect to z. So what is this? This is actually a scalar. So if you'll remember from the matrix vector algebra introduction video that we did, a dot product, the outcome or the output of a dot product is a scalar. It's a single number. And so here the divergence, remember with the gradient operator, we go from a scalar valued field to a vector valued field, which is the gradient. With the divergence, we actually go from a vector valued field to a scalar valued field. So now at every location in space, we've calculated the divergence of f, which is going to be a single number. It's going to be a scalar field at each point in space. So divergence, very different from the gradient. Now divergence is actually going to be a really important quantity for us because it's going to be related to field lines and field lines coming into and out of a volume. We'll get more into that later when we talk about the divergence theorem, for example. But for now, that's just the basic definition. It's the dot product of the gradient vector with a vector valued field at each point in space. We sum those up, we get a scalar valued field. Now, we also want to talk about the curl, and I'll go ahead and just leave this up for now because it's going to be very similar. So we're going to define the curl of a vector, del cross f. So now instead of del dot f, it's going to be del cross f. Where cross here is the cross product. It's the cross product of one vector with another. Now, the cross product is not nearly as intuitive, just to easily understand as the other quantities are, I think, just in my own opinion. You probably remember from physics, people talk about cross product as maybe you turning a screw in a particular direction, clockwise or counterclockwise, and the direction of motion as you're turning a wrench to turn the screw or the bolt, that direction of motion is going to be perpendicular to the direction that you're turning. And so that's kind of where this cross product comes into play. It's motion. In the case of curl specifically, it's going to be solenoidal or torsional motion around another vector field. Again, not the most intuitive thing, at least in my opinion, but we can write down what it is and we can write it down mathematically. And this one I always have a hard time remembering, so I have to go ahead and just check back in the book about the definition of the curl of the vector. And what I'm going to do is I'm going to write this. There's a few different ways to write this. You can check the book. This is page 366 and 367 in the Blakely textbook. I'm going to write it as the determinant. So we can write these quantities as the determinant of a matrix. Where in this case we have I hat, j hat, k hat on the top. We're going to have our gradient operator in this middle row. Again, you'll notice it's partial derivatives here, so we're just taking the derivative with respect to x, just the derivative with respect to y, just the derivative with respect to z. And then finally on the bottom we have the components of f. So this is a 3x3 kind of matrix of numbers, and we're going to take the determinant of that matrix of numbers. And again, the equations are written out in the textbook. I'm not going to write those out for you. What does our book say? One way to visualize the curl of a vector is to imagine a paddle wheel placed in a fluid that flows in accordance with the vector. The paddle wheel will rotate if the curl of the vector is non-zero. The curl of a vector is sometimes called the vorticity of the vector, and a vector field with non-zero curl is called a rotational or vortex field. If the curl is zero, and here's the important one for us, if the curl is zero, the vector field is said to be irrotational or conservative. And we're going to be talking about irrotational and conservative fields where the curl of a vector field is equal to zero. Now, why would that be important? Well, because again, maybe it's not so clear from here, but basically, for those of you who may remember from linear algebra, in order to calculate what this is, you would sort of cross multiply through diagonal entries. And so you'll end up with a bunch of terms multiplied by each other and then added up together. And so what it means if the curl of the field is zero is that we can set that all those terms, all the products that we would calculate when we calculate that determinant, we can set those equal to zero, and then we can say things about what those different quantities must be. So again, we'll talk about this in more detail for the specific cases that we're going to look at with gravitational and magnetic fields. But for now, here's our definition of the curl, and it's kind of a rotational field around another vector field. So here we have a vector. We're taking a cross product of another vector, a vector field, and that result is going to end up being another vector field. So it's a vector field around another vector field. The divergence is a scalar field based on a vector field. So we take the divergence of a vector field, we get a scalar field. And the gradient is, we're going to take the gradient of a scalar field, we'll end up with a vector field. So again, a little bit confusing here probably, but again, hopefully this will start to make more sense as we dive into the details. Okay, so that's gradient, divergence, curl. We'll talk a lot more about these when we get into the details of gravity and magnetic fields, and I will see you in the next video.